Hi everyone, welcome to tutorial 4. Today is really the first tutorial where we actually talk about some real deep learning, at least in terms of a model. So we'll talk about convolutional networks. Specifically, we'll show convolutional layers, how they're defined and how they work. We'll talk about pooling layers, which is a core part of the architecture, and different architectures, at least briefly, and we'll show some additional examples of spatial classification and residual networks. Okay, so what we saw so far, at least last time, was that we had this model called the multi-layer perceptron, which is composed of layers of neurons. Each neuron is computing a weighted sum of its inputs and applying some nonlinearity. Okay, so we started with logistic regression, then we expanded to MLPs. And this is a nice model, has very nice properties. You can use it for classification, for regression, for multi-class cases. And this is the kind of the definition that we saw of the model. We call that it's fully differentiable, so we can optimize it easily. And additionally, it's a very powerful model in the sense that it can approximate basically any function. Okay, so what's wrong with it? Well, specifically for image classification, it has some severe limitations, this model. So I wonder if anyone has an idea, like kind of the main limitation of having a fully connected layer in front of an image. Think about what we did last time, yeah? Okay, it's large, so in terms of input features, so if you think about what we did last time or so far, we took an image and flattened it and just treated all the pixels like they were separate features. Okay, so that is probably not a good idea if you're trying to kind of conserve weights. For example, if you have a small MNIST image like we saw, we had 784 weights per neuron in the input layer of our MLP. But if you kind of expand it to larger color images, then just per neuron in your first fully connected layer of your MLP, you will have 3 million weights. Again, per neuron. So that's a core limitation of MLPs for image classification. And again, the problem with having so many parameters, at least one problem, besides the optimization issue, is the fact that you're much more likely to overfit. So if you have an MLP, regardless if you have multiple layers or many neurons in one layer, you're just increasing your parameters. And if you have an image as an input, then like you saw, you have lots of parameters in this case. And moreover, the fact that you're using a fully connected layer and connecting to every single neuron, to every single pixel, means that you're very, very sensitive to any translation. If you move your image by a few pixels, then your learned weights will be completely irrelevant, because each neuron is basically looking at the whole image and learning something about the exact position of pixels in that image. Okay, so these are the major limitations of MLP models for images, but we still want to use kind of deep neural networks because of the nice properties that we saw, that they learn these nonlinear hierarchical transformations of the input, which after you apply all these nonlinear transformations, basically you can do some linear classifier in a very high dimension, and that way you can classify your data. So what we actually do with images is we have these layers called convolutional layers, which we'll now explain how they work. So we'll look at them. I like to think of them like in 3 different ways. At least that's what I'll show. So I'll start with something very non-formal, just kind of an intuitive explanation, and then go to something a bit more formal. So like the most intuitive way I can think about it as something kind of as an extension of an MLP is this, what I call this, like a structural view. So it's just for intuition. It's not really how it's implemented, but just like as an intuition to understand what's going on. You can think about it as composed also of neurons, just like an MLP, but with some distinctions that I will now explain. So instead of having each neuron connected to all the input features, like all the pixels in the image. Each neuron will be connected to a small region of the input, like only a subset of the features. And instead of imagining your neurons as stacked in a 1D layer, imagine them as being in a kind of 3D grid. Okay, and again, each neuron is connected to something and calculating some number. And the crucial element is that if the neurons are in the same depth in this grid, represented here by the colors, they have the same weights. Parameters W and B. Okay, remember the W is the weighting of the inputs and the B is the bias. So for example, in this structural view, you have this 3D volume of neurons where each depth slice, different color, represents the fact that these neurons have the same weights. Okay, and additionally, each neuron is looking at a small section of the input. Okay, so two important things about this, that they operate and produce volumes, because since now we think about them as stacked in 3D, each one of them is producing a number. Our output will also be kind of a 3D tensor. Okay, and each neuron here is spatially local. So like I said, it only looks at a small subset of its input. So this, for example, is an input image, and this neuron is only connected to part of it, but it is looking at the whole depth. So here the depth is 3. See the depth? So we have 3 color channels. This neuron is looking at all that depth, all the input depth, 3 color channels, but on a small extent. Okay, and behind it in this grid we have other neurons that are looking at the exact same location, but they have different weights. That's the concept of the colors here. Okay, so yeah. No, this is one layer. This is kind of, I'm explaining structurally the output of one convolutional layer. Again, this is just for intuition. It's not really what's going on. Yeah.
Can you explain?
Sorry? Yeah, this is one layer, exactly. This whole thing is one layer. Each of these neurons will calculate one number based on some part of the input. The whole 3D tensor full of these numbers calculated by the neurons is a result of this one layer. Okay? Yeah.
So each layer in the input, each layer in the depth have the same weights for
the input has, for example, 3 depth slices, like color channels, and here you have different neurons stacked also in depth slices. Each of them have different parameterizations, but they're looking at the same area.
So it's like output channels?
Yes. I'll show it in a second. So that's kind of one way to understand it, as at least in the case of images. It's not that convolutional layers only operate on images or they only operate on 3D tensors or anything, but this is just kind of an intuitive way to understand what the transformation is doing, kind of taking a 3D volume to a 3D volume by looking at these different, looking all the time at the whole depth, here, the whole depth, but at different locations. So that's kind of the structural way. Another way to look at it is this filter-based view. Okay, so now what we'll imagine is that we're looking at, this is our output here, and we'll imagine that each depth slice of this output, represented by different colors here, is a filtered version of the input volume. So imagine that you have different filters. So these are 3 by 3 by 3 filters. Imagine that you're sliding them inside your input volume. So again, they're looking at, each filter is looking at the small 3 by 3 region, but the whole depth, so it's 3 by 3 by 3. You're sliding it over the whole input, and each time you slide it, you get one number. It's an inner product. So that's why you have this 2D slice here. So for each filter, you get a separate 2D slice. That's what the colors show. Okay, so this is another way to look at it. So this is more close to convolutions, because as I will show, this is exactly what's happening. So imagine you're sliding some kind of filter, which just is a small kind of template over your image, and you have this response, because at each point you're calculating the inner product between your filter and that slice of the image.
Each filter, by saying filter, you mean each it's a different weight?
Yes.
The difference between the filters is a different weight.
Yeah, exactly. And you learn them, of course. Yeah.
So this output
This
When
this
we had before
yeah this
layers, same color layers.
so
This is one output.
exactly.
One layer.
So this image of this 0 might be, sorry, it might be this white 2D slice, or it might be this black 2D slice. It's one of those.
And the colors before the previous example.
This is just the same idea, same thing, just different way to look at it. This is imagining like you have a stack of neurons like in an MLP, and each one is connecting to something.
One circle, right?
One what?
Show that it's one circle, it's not one circle.
Yeah, this is just showing one set of neurons that are looking at the same region. Okay, these neurons have the same input region but different weights, right? And these neurons have kind of the depth slice is looking at different input regions. So depending on what's more intuitive for you, either of these views can work. Okay, but like formally, if you want to think about it more formally, then you can write it like so. So if you have an input tensor, let's say it's of this shape, C in, H in, W. So C is the number of input channels. Let's say it's an image, so it's 3. H in and W in are the spatial dimensions. So let's say it's a 200 by 200 image. So H is 200, W is 200. So a convolutional layer would produce a different tensor of this shape. Okay, so it's also a 3D volume. Okay, and basically what you see here is that you have a convolutional filter operating on every single filter input kind of a feature map, which is a 2D plane of your input, and you're creating these output feature maps. So for example here, J is the output feature map or output slice. So Yj would be 2D, and you have C out of those. Okay, and each one of them is computed by a convolution. So this is kind of the formal way, but if you look at the previous explanation, then it's much more intuitive to really imagine these kind of 3D filters going over your input space, especially if it's an image. Okay, any questions so far? No, I didn't. Said nothing about downsampling so far. There's no downsampling in the convolutional layer, as I explained it so far. Okay, there's something else. So just if you kind of recall what convolution is actually doing, it's kind of you kind of slide a flipped filter over your input, and that's the explanation of this sliding filter. So this is in 1D. So at each point of the output j, you're computing the sum over the whole input and filter. So an important property of convolutions is that they're linear, and they're also shift equivariant. Anyone remember what that means? So what does linear mean? What does it mean that it's a linear operator? Sorry? Differentiable. It can be implemented as a matrix multiplication. And the fact that it's shift equivariant, what does that mean? Yes, toplets, but more intuitively? Yes. So if you shift equivariant, so if you shift the input, you get a shifted output by the same amount. It's not shift invariant, it's equivariant. So again, it can be represented and implemented. Actually, what's going on is you really implement it by these toplets matrices. For each filter, you have this kind of a matrix multiplication that determines how this is how you perform the convolution underneath. Okay, so that's kind of the three ways to look at it. You can look at it kind of structurally similar to an MLP, but in 3D. You can look at it as a bunch of filters that are also 3D filters because they look at the whole depth that are sliding. And you can really just look at it as a bunch of matrix multiplications where you multiply with toplets matrices. Now, let's talk about more specifically the hyperparameters of these convolutional layers. So like we said, let's say we have this input volume shape C in, H in, W in. And we define now for each convolutional layer that we have, we define our number of kernels. So when I say kernels, I also mean filters. The kernels, it's the same synonyms in this case. So we have a number of kernels K. So each layer does not have, as you saw, does not have one kernel. It has multiple kernels. That's why you had multiple depth slices with different colors.
Number of channels?
Yes, it defines the number of channels in the output, exactly. Like you saw in that image where you had multiple filters of different colors and you had the different depth slices of the same colors. So you have a number of kernels, K. Each kernel has its own spatial extent. In this case, we'll call it F, and we'll imagine the filters are always F by F. So F can be 3, so you have 3 by 3 kernels. We'll imagine that it's always 3 by 3, but it can also be 3 by 4 or whatever. We have something called stride, which is the spatial distance where you, between consecutive applications, I'll show it in a second. It basically means that you're jumping your filter by, not by one, but by larger steps. We have padding, which means adding zeros around the input layer, or input. You can pad with whatever. Yeah, you can pad with flipped, mirrored, whatever you want, but the number of pixels or features that you add in each dimension is p, and dilation, which is best explained visually. So I'll show it just in a second. So let's look at these nice animations here to explain what's going on with these parameters. So you have in these animations, let's just look at the leftmost one here. So you have the input is in blue, okay, and the shaded part is a convolutional filter going over the input, and the green part is the computed output. So for example, here you can see that applying a 3 by 3 filter, shaded filter here, on this 4 by 4 input provides you with a 2 by 2 output because the filter doesn't have room to move anymore. It gets kind of stuck at the end, right, when you move it. So this is one example where you don't have padding. If you, for example, in this example, add padding of 1, then you add a dimension of 1 with zeros around, so now your filter has more places to move. In this example here, you can see that the filter is jumping by stride 2. So it's skipping each time 1 pixel in the input plane. And this is an example with dilation where you apply the filter to space, kind of not to consecutive regions in the input, you space out your filter over the input. Okay, so each of these parameters has kind of a different use and function. But some of them have important properties. For example, you can see that the second combination here, where the filter was 3 by 3, we added one pixel of padding, and we had a stride of 1 without dilation, so D is 1. We got the same spatial extent between the input and the output. So we had, in this case, 5 by 5 input, and we got a 5 by 5 output. Okay, so sometimes you can preserve the spatial dimensions, and sometimes your convolution may actually shrink your spatial dimensions. Yeah. The main motivation is to increase something called the receptive field, which I'll show it down. I'll show what the receptive field is. Yeah, without adding more depth, basically, to your model, because receptive field increases with depth, as you will see soon, but this is a way to increase it much faster. It's one way. Yeah. The kernels. Here in this animation, the shaded area. Imagine the shaded area is a 3 by 3 set of numbers that you multiply by the numbers from the underlying blue area. And each time you multiply, you get one number, which is computing your output. Okay? So in the convolutional layer, you have multiple kernels like that, and you apply each of those kernels to your input. But remember that usually your input has multiple channels, so you will apply your filters across all those channels. It's not shown here, so here it's just 2D. Yeah. D equals 2 here, because you don't have any more room to move. When you increase dilation and you don't add padding, for example, then your filter just, it gets to the end here and doesn't move anymore. See the shaded area gets stuck? Now I'll show just the formula to explain it. So this is a kind of a formula that given a set of hyperparameters, remember that you have your convolutional kernels, so your kernels will be tensors of this shape. Okay, because they operate on all the input channels and they're f by f. So for example, 3 by 3 by 3 if your input has 3 channels. Okay, and your output dimensions will be given by this formula. This I really copied it directly from, for example, from the PyTorch documentation for this set of hyperparameters. So you can see, just kind of looking at it, what everything is doing. For example, S is the stride. So you can see when you increase the stride, you divide. Let's say you have stride of 2, you're dividing the spatial extent by 2. Okay, because you're jumping by 2 pixels each time. Your filter has less places to be in. So your output will be smaller by 2, by a factor of 2. But increasing padding is here, so it will increase your output dimension. If you have lots of padding, your filter will move across the whole padded input, and you'll increase your output dimension. Now, increasing both dilation or filter size, because of this minus here, dilation, you can see dilation and filter size will shrink your spatial extent. Okay, so it's just kind of a formula to see what you saw in these animations. Kind of if you look at them and consider these formulas, you can see what's going on. But remember that always the output will be k. The output channels will always be the number of convolutional filters that you had. So you just define how many convolutional filters you have in your convolutional layer. You say it's k. Your output will have k channels. Okay, the spatial extent of the output will be defined like that, but you will always have k channels as you defined. All right. So how many parameters? Remember that we saw, like in an MLP, when you connect an MLP to an image, you have lots of parameters because of those full connections between each neuron and all the inputs. So how many parameters do you think convolutional layer has? Sorry. Let's think about it. So we have k kernels, right? How many parameters does each of these kernels have? Let's say we have f squared, but what about the input dimension, input depth? Okay. Yeah, okay, so you're right. So basically, you have k kernels, and for each kernel, the number of parameters is the size of the kernel, okay, number of parameters in the kernel, which is defined by the spatial extent, f squared here, and Cin, which is the number of input channels, because you have, your kernel is also 3D, and it's operating on all the input channels. Okay, and you have +1 for the bias term, because you also have bias. Okay, that's it. So for example, if your input image is like before, 1000 by 1000 by 3, and the first convolutional layer has 10 kernels of size 5 by 5, you can calculate the number of parameters to be 760 instead of the 3 million that we saw. Okay, so this is kind of the input on the image. Yeah. No, I didn't show it has the same power. I didn't say it has less power, but specifically for images, due to the properties of the image, where you, for example, don't care about the exact location of the cat in the image, you want to recognize that it's a cat, then this kind of adds a kind of a prior knowledge of your input, and it's actually a good idea to do it. But yeah, of course, you have much less parameters, so it's a less powerful model. No, the whole idea is that these are trainable parameters. So you're learning the filters end to end. You have no idea what you're starting with, just random filters, and you're learning the filters that will allow you to, for example, classify between cats and dogs at the end. Yeah.
As long as I keep the dimensions of C out of the next channels in the layer the same size, can I choose different kernels, like one with dilation, one without, one with stride? As long as I keep the dimensions of C out the same, can I choose a different?
Probably yes. Probably yes. Technically, like in PyTorch, no. PyTorch, you have to specify the hyperparameters per layer. But like if you implement it yourself, then yes, and you create somehow the same spatial extent, then you can apply different filters with different parameters, and then just squash them together and say that's your output. Okay, so let's keep going. Let's just see a quick example of a conv layer using PyTorch. I'm just loading a data set of C410 images. Again, doesn't matter what the data is. So this is a one input image. Small thing that I did this on squeeze here. I add, after I take my image, I add a batch dimension. So I have this 4D tensor of a batch size and 3 color channels and then the spatial extent of the image. This is just because this is how the PyTorch conv layers expect the input to be shaped. They expect the first dimension to be batch and then your 3D tensor. Okay? So let's just, this is just a function to print the number of parameters. Let's look.
What does batch mean in this case?
It's just the number of images that you have, that you're giving together into the model. So you can, where was that? Usually you use a batch size of some, I don't know, tens of images, hundreds of images sometimes. This could be, for example, 128.
This is your training set? What do you mean by images?
No, I'm taking my training set. Let's say it has 1,000,000 images. When I train my model, I will work on batches of images. Each time I take randomly 100 images.
Oh, this
And
is the batch size.
yeah, and then I will have 100 by 3 by 32 by 32. And I give that whole batch to my convolutional layer.
So it's the batch size.
Yeah, it's the batch size.
The mini batch.
Yeah. Okay, so I just need this here because otherwise I won't have the right dimensions to apply the PyTorch conv layer on the input. Yeah. So this is my the PyTorch conv layer. This is how you define it. Like you can see, it has all the hyperparameters that we said. There's also dilation. I didn't write it here, but you define the number of input channels, the number of output channels. So this is their K. This is K. Padding. This is the P. Kernel size. This is F. Okay, and stride. This is S. And there's also dilation. I just didn't write it here because I didn't have room. These are the main parameters that you use. So what I did here, I calculated the number of parameters just by counting. So we have 280 parameters. Okay, it actually makes sense because we have 10 output channels, so 10 kernels. Each kernel has a spatial extent of 3. So it's 3 by 3, and we have 3 input channels, which is coming here from the image. Okay, so if this is our input shape, look at the output shape after the first conv layer. So in this case, since we selected the parameters in a way that preserves the spatial extent, like you saw in the animations, okay, so padding 1, kernel 3, stride 1 will preserve your spatial dimensions. That's why we got here the same spatial extent, but 10 output channels. Okay, so it's exactly like I showed in the structural part or the filter part. You get these 10 2D planes. Each 2D plane is 32 by 32. In each 2D plane represents the output of one of the filters. Yeah. When you initialize the layer, yes. It's completely random, but you learn the filters. I'll show it soon. Okay, so let's say now I have another conv layer. I have this conv2. It's taking an input. It's taking 10 input channels and it's converting them to 20 output channels. Okay, and now I'm taking different parameters. So no padding, a larger kernel, and a stride of 2. Okay, and now after the second conv layer, I have 20 output channels and my spatial extent was decreased from 32 by 32 to 14 by 14 due to the larger kernel size and larger stride with no padding. So now I have no padding and I have a larger filter and I'm jumping it by a stride of 2. Okay, so my filter will get stuck somewhere and I will get a smaller spatial extent. And now I have also much more parameters in this layer since we have 20 kernels this time and each kernel is much larger and it's also operating on 10 input channels. So you have 6 by 6 by 10 plus 1 times 20. So that's the number of parameters. Okay.
So now during your learning process, will it calculate the loss? I mean, it will change the weights per each, and also will change the parameters of the how do you call those parameters?
Filter parameters.
This convolutional parameters.
It's exactly like train the MLP, you have this W weight matrix, right? And you're calculating the gradient of the loss with respect to that and updating that. So it's exactly the same thing. Each of these fields.
You have weights and type, you can say. I have a stride of 2 and the kernel.
But that doesn't affect anything. It's the same parameters. I just apply them differently. If I have a different stride.
Oh, you do not randomize them? You do not let him like learning the.
No, these are hyperparameters. If you want to find the best stride or whatever, it's part of your architecture. You can run a hyperparameter search to find that. But it's not related to optimization. When you optimize to find the best kernels, or where you update your kernels during gradient descent, it doesn't matter if you apply the stride of 2, because you had the same weights, you just use them differently. You just use them with a stride or with dilation. But
there's no like optimization of second layer should be stride of 2 depending of reversal.
That's hyperparameters. It's
You predefine them?
You predefine them, and if you want to search over them, you have to use techniques for hyperparameter optimization. No. Okay, but note something interesting. We never specified the dimension of the input. We never said that we have input images of 32 by 32. Okay, we just said we have an input number of channels 3. Okay, that's important. We'll see why later. Let's look at pooling. Try to move a bit faster now. So another way to reduce the spatial extent is using pooling, not just striding. So pooling just means that you're looking at these pooling kernels. Let's say you have a 2 by 2 pooling kernel and a stride of 2, like in this example. And you do some kind of reduction operation, like max. So in each 2 by 2 region here, we'll take the maximum. So this is a feature map, output of one kernel. Let's say we have 2 by 2 and a stride of 2. So we're taking the maximum and we're getting this reduced size with maximum activation. This is a max pooling layer. Okay, so first of all, one question is why do this? Okay, why do this at all? So one reason is to rapidly increase what's called the receptive field. So this is it was asked before. This is one reason to use pooling. So it's one way to do it. Like a striding and dilation, it increases the receptive field. So what is the receptive field? Let's say we are here in layer 3. The receptive field of this element here, this element in this output feature map, is the parts of the input that affect it. So you can see the receptive field kind of grows. When you go deeper, it grows because of the way these convolutions are defined. So each output element here is affected by this region, and each element here is affected by a different region. So you kind of have a growing receptive field. But when you shrink the spatial dimensions, let's say I apply pooling and I take 4 pixels and I shrink them together, then basically I'm increasing my receptive field faster. And this is a good idea because you take the maximum. If it's a max pooling layer, you take the maximum of these, for example, 4 pixels here.
The maximum 4.
The maximum between these 4. So these are 4 pixels in one feature map. You're just taking the maximum between them. And you have a 2 by 2 kind of spatial extent that you're moving around. You're jumping it with a stride of 2. At each location, you're taking the maximum of what you see, and that's the output. All right. So basically, we want our successive conv layers to be affected by larger parts of the input image. And what we're learning in this way is kind of a hierarchy of visual features, where the first layers are learning simple features, and the deeper layers are combining them, which I'll show it in a second in a different visualization. And a different reason to use pooling. Like we said, the convolutions are shift equivariant, but adding pooling gives you some invariance. Okay, so for example, if you have this pooling, then you're actually invariant to small translations, since you're taking the maximum. Okay, it doesn't really matter if this pixel was here or here. So for small translations, pooling creates this kind of a shift invariance. And another type is that if you pool across feature maps, so you don't you take a different, you pool across your different channels, okay, then you can produce invariants to learn transformations, because each of these feature maps is a different filter on your input. Okay, so you can pool across them. And for example, here's an example of, this is a feature map that was maximally activated by this orientation. Okay, so when you pool across them, it doesn't matter whether the input was oriented, as long as one of the feature maps was activated or maximally activated by this type of orientation, then the output here will be the same. It will have a large response in the pooling unit. So basically, you can say you're kind of invariant to some small transformations.
What do you mean by activate?
I mean that you had a strong response to your filter. Like when you used your filter over the input, you had a strong response. Remember, the filter is just doing inner products. So when it matches the pattern in the filter, you get a stronger response. Okay? I'll show a visualization just now. This is just an example of how to use 2D pooling. It's not very interesting. You just see that here, after I apply 2 convolutions to my input, and then I apply my pooling, I get a reduced spatial extent. Okay? Because I define it with a kernel of 2 and stride of 2. So for each 4 pixels, I took the maximum one. Okay. Let's talk about network architectures a bit. Just how to, what's the place of these convolutional pooling layers? So usually, what you do to create your model, you stack multiple layers of convolutions, where each convolution here is followed by some nonlinearity. Because again, this is a linear operation. You still need nonlinearities to get any kind of deep nonlinear features. So you use multiple convolutions and then pooling, and then you kind of repeat this in these blocks to create these deep hierarchical features. And in the end, usually in most models, what you have is some kind of MLP in the end. So in this case, for example, we would have a few fully connected layers and a softmax to, for example, get class probabilities. Okay? So kind of intuitively, what do you think is the purpose of this structure? Pre-process? Well, you process the data, yes, but think about this like, this is the input. You're doing this whole forward pass, okay? And then this is your model, so you're backpropping through the whole thing. The idea is to basically use these convolutions to extract features that are relevant for images. So you're learning filters, local filters or local features, sorry, of the input. And these fully connected layers at the end is just basically an MLP that's now looking at the result of all this feature extraction from your image. So when you learn this end to end, you're learning the filters to extract features from your image, and then you're applying an MLP not on the original pixels. You're applying the MLP on these extracted nonlinear features that depend on these learned filters. Okay, so now your final MLP, which will actually be used for classification, is working on some much more powerful representation. Yes.
After you extract the feature, is that like more sparse?
I wouldn't say it's more sparse. It's just it's completely different. It's just it's features that are extracted from the image. I'll show you a visualization just in a few slides. I just want to keep going because we don't have much more time. So, like I said, there's lots of things that you need to consider. So this is just a basic template for an architecture, but you still need to define for each conv layer the number of kernels, the size of the kernels, some different normalization that you want to use to improve the training, or if you want to use dropout. Okay, maybe you don't want to use fully connected layers at all, which we'll see in a second. And also, usually you add skip connections, which we'll also see in a second. Just want to make sure we have enough time. So this is just a comparison of some architectures. I want to skip it. I want to show this example. This is a nice visualization from a paper from 2013 that kind of visualizes what these filters are learning. So what they're showing here is kind of image regions that maximally activate learned filters in different layers of the convolutional network. So you can see, for example, in the first layers, what you get, these filters that you're learning are doing very basic things. They have these diagonal straight lines or just straight lines. So they're activated by edges, for example, in the images. Okay? And when you go deeper, you have kind of more complex filters that combine the filters from the previous layers or the features from the previous layers, and they're activated by more complex patterns. Okay? So here you have more complex patterns like circles or textures, and these are the things that maximally activate filters in layer 2. And when you go to layer 3, you have, for example, even more complex patterns, even more complex textures that are maximally activating the learned features. So this is kind of showing the hierarchical nature of the fact that you're extracting features, and then the next layer is extracting the features from the features, and so on. So you're kind of combining, using these basic building blocks of the first layers, more complex building blocks in the deeper layers. For example, you might in a very deep layer in the network get a filter that's activated by faces of people or ears of cats. Okay, so if you have something that's maximally activated by ears of a cat, then you have an MLP. Your MLP will notice that, okay, I have a feature here that says we have a cat ear, so I might predict that it's a cat. Okay, when I train my MLP at the end using these kind of deep features.
Can we then just take this specific layer and use it with MLP, or we need all those in front of it?
You need the whole thing, but you can use it as a general purpose feature extraction, then use it with other things, not put an MLP at the end.
Is it learned or is it engineered like?
No, this is learned. Everything is learned, end to end. You initialize your weights at random.
What the difference in mechanical terms between the MLP and the end and this feature extraction? This is the same backpropagation, no?
The backpropagation is the same, but the assumptions are completely different. Since the fact that you're using these convolutions means that you're assuming something about your input. You're assuming that features are local. So if you're learning a filter that detects edges, it detects edges no matter where they are. And then deeper layers combine these detections to, for example, detect a pattern or a circle. And at the end, when you have all these features of circles and cat ears and eyes and whatever, then your MLP classifier has a much easier job of classifying the image because it's using these deep features. Okay, so we're kind of running out of time. I want to show an example of implementing a convolutional network. So let's implement this network called Linnet. It's arguably one of the first successful CNN models. What you can see here is you're taking this. The Linnet architecture is taking an input. It's producing 6 feature maps. Okay, so it has 6 output channels here, and then it's doing pooling. So it's remaining with 6. Then it's doing another convolutional layer with 10 kernels, and then it's doing pooling again, and then it's applying 2 fully connected layers. Okay. So let's look at an implementation of Linnet with PyTorch. So I split this into 2 parts: the feature extractor, which is just a sequential, so it's a sequence of modules, and a classifier, which is my MLP at the end. And you'll see why I split it like that in a second. But basically, this is just straight up copying the diagram that you saw here. So I'm starting with 3 input channels, for example. I have a convolutional layer that will give me 6 output channels with 5 by 5 filters. Again, this is exactly what was drawn here. Okay. And then I'm doing pooling. And then I have 6 input channels because this was the output channels here. So I have 6 here, outputting 16 channels, and then doing pooling again. Okay, so like you see here, we're starting with 3, going to 6, then going to 16. Okay, and then doing pooling.
You do the non-linearity after each convolution.
Yeah, I added this value here. You have to have non-linearities, otherwise your model is just linear. Then I have this classifier part. So I have this fully connected layer. It's taking 16 by 5 by 5 features. So why 16 by 5 by 5? So again, I have 16 output channels. and 5 by 5 is the spatial extent that I got to. I had to calculate this, but this is the shape of the volume. So I have 16 by 5 by 5 features in the input, and I want to transform them to 120 features just because it says 120 here, okay? And then to 84, and then to 10. Okay, so then I have another fully connected from 120 to 84, and then from 84 to 10. When I do the forward pass, I apply my feature extractor, so I get this volume. Then I squash the result, so I have a 3D tensor. I'm squashing it, okay, just to make it flat, so I can apply the fully connected layer, and then I give this flat features to my classifier, and it's applying these 3 fully connected layers.
So what is the shape after the squashing?
The whole model after the whole output will be 10. Shape 1 by 10.
No, just after the...
After squashing, then you have 1 by 16 by 5 by 5. Whatever this number is, you have that. Okay, let's look at the model. So this is just a printout of the model. And here I'm applying it to my input image, and you can see the output is shape 1 by 10, which is what we expect. We have 10 output classes. Okay, not very interesting. Now let's look at the more interesting thing. The fact that, like I mentioned before, we never actually specified the input image size, okay, when we implemented our network. So the question is for you, do you think that we could have used this network, this LeNet that we just implemented on images of any size? I never specified the image size, I just said we had 3 input channels. So will it work on any image size? No, why not?
Because the filters are set and you expect some kind of dimension, so if you put...
The filters don't care. They look at 3 by 3 by 3. They don't care. They do that.
Yeah, but they'll miss if the image is very big. I don't know, they might miss something or...
It's not because of the filters. Fully connected, exactly. The last part of the network, we squashed everything to 16 by 5 by 5, and we hard-coded that number into the input of the fully connected layer. Okay? And that number, 16 by 5 by 5, depends on the input size, because we took 32 by 32 and applied 2 pooling layers, which decreased the dimensions. And that's why we got 5 by 5 as a spatial extent there. So that really depends on input. So let's see. Just to prove it, if I take a larger image, so it's now 3 by 64 by 64, and I give it to my LeNet, I get a size mismatch. Doesn't work. I can't do that because of the fully connected layer. Okay, so it's really that's the problem. But the thing is, we can replace them just by more convolutional layers. So if you think about it, what would happen if you have, let's say this is your input tensor and this is your filter. Imagine what would happen if the size of the kernel here would cover the whole spatial extent. Okay, it would be over the whole thing. What would happen? It won't move, right? So you'd get one number from the whole volume because it will just sit there and won't be able to move. So if I had multiple filters with the whole spatial extent, I would just get k numbers as an output. And similarly, if I have 1 by 1 kernels, let's say I have k kernels of size 1 by 1, okay? You can similarly imagine since it's actually 1 by 1 by the input channels, right? So what you're doing with 1 by 1 convolutions is you're combining all the input channels. Okay, so both of these definitions make sense. You can use the whole spatial extent and you can use 1 by 1 kernels. And if you do that, then you can create this fully convolutional version of LeNet. Okay, so what I did, remember, I had this feature extractor part and classifier part. So the feature extractor part is the same. I'm just overriding the class. I'm creating a subclass. My feature extractor is the same, and just overriding this classifier with a different sequential part, which is now made of convolutions instead of fully connected parts. Okay, so remember, we had a feature map of this shape, 16 channels by 5 by 5. Okay, so the thing I'm going to do now is create a convolutional layer from 16 channels to 120 output channels, but the size of the filter will be 5 by 5. So it covers the whole spatial extent. So each of these 120 filters will operate on the whole input tensor and produce one number. So it'll create 120 numbers with a shape of 1 by 1. Okay? And after that, I can apply 84 other kernels of shape 1 by 1. And then I get 84 numbers, exactly like a fully connected layer. And then I apply 10 kernels, again of shape 1 by 1, and I get 10 numbers. So again, this is my conversion from fully connected to convolutional. Yes?
Fully connected, fully convolutional, your goal is to be able to input image any size, and so it still works.
Not exactly any size, but at least larger images.
Okay, so what you are doing, you're saying before the fully connected part, I'll insert a convolution.
Not before, instead. I replace the fully connected part. Yeah. I just have to keep going because we're kind of running out of time. But we can talk after class. So let's look at the forward pass here. If I take my original image, now I apply my fully convolutional network, I get kind of a different shape now. It's 1 by 10 by 1 by 1. And if I apply my larger image, okay, I get this output shape. So it's 1 by 10. Remember, I have 10 output classes, but what are these extra dimensions? What does it mean that I got 1 by 10? 10 is the output classes, and a spatial extent of 9 by 9. So what does this mean? Any ideas? Okay, I'll tell you since we're running out of time. So imagine that now your whole network is just like one big convolutional filter. You're sliding it over the input. If you take the original input size, then it just fits exactly, and you get this output shape. But if you have a larger image, then you have more places to put the whole network. And each time you place your network on your input, you get these 10 numbers which represent the class probability, if you put a softmax or class scores of that location, okay? So essentially what you get is a kind of heat map. For example, if this is my larger image, and I'm looking at the class, let's say class 3 is a cat. So what my output spatial extent will mean is basically the heat map or the score of a cat in each location where I put my whole convolutional network over the image. So this is kind of a bit more powerful also than using fully connected layers. It's kind of it's not a classification of each pixel. The spatial extent here is not the same as that necessarily. It can be much smaller, but it's a heat map that shows where there might be a cat in the input. Because remember, I got a smaller spatial extent, so each pixel.
Back to pixels.
Yeah, there is a receptive
the
field.
region of pixels.
Exactly. It translates to a region of pixels where there could be a cat.
And then you can make a bounding box.
Yeah, this is one idea. Okay, so we're out of time. So there's just another last part.
So for additional information about tagging, you also find the location.
This is one way to do it. So there's a last part. You can look at it afterwards in the notebook. So thanks. Okay, so if you remember last time in the tutorial we talked about convolutional neural networks, and we saw kind of how they work and the idea behind them, and we saw this nice example of fully convolutional networks. And okay, so the last part is about residual networks, which is a way of getting deeper convolutional networks. So the idea is that kind of you want more depth generally in this whole deep learning thing. It seems that if you have deeper models, you can learn more complex features. And there's lots of empiric results that show that somehow magically even though the models are much deeper and they have more parameters, you can still optimize over them. And actually, again, empirical results show that it somehow improves generalization when you have larger models. So we want to go deeper, but the question is how deep can we actually go without kind of destroying our ability to keep updating the weights. So, but think about like from the theory part, if you add an additional layer, kind of in theory, should it be able to learn less well or not? So kind of explain it here. In theory, if you add another layer, you should get kind of at least the same. If you had like the best possible optimizer, you had the kind of a perfect optimization strategy. Adding another layer should not affect your result. I'm not talking about that. I'm saying if you let's it improves overfitting. Okay, let's say you just want to fit your data. Adding another layer shouldn't harm that if you have a perfect optimizer.
Like if you add more and more layers, then you are risking.
Yeah, you are risking overfitting. Yeah.
So it could affect you when you
No, but
test.
if you ignore, I'm not talking about the concept of generalization. I'm talking about something else. The representation of the model. Like you're increasing the model, so it should be able to represent more, not less. Okay. So if you can get to a specific accuracy, then you should be able to get it with a larger model. Okay. It can always just in the kind of extreme case, you can add more layers and they can just learn identity maps. They don't have to actually do anything. You just increase the capacity. You shouldn't be able to kind of reduce it. But what actually happens is that you have these effects that kind of harm training because we don't have this perfect optimizer. We optimize with gradient descent. Okay, and we have these effects of vanishing gradients that you saw in the lectures. And generally, since our optimizer is not perfect, then we do care that the parameter space increases the space. So when we add parameters, we do have a harder time to optimize. And in practice, so this is from a paper that introduced this residual networks. So in practice, even though just adding layers should allow you to train to the same accuracy, that's not what you see. Even the training error does not reach the same level, not just the test. So this is a kind of a naive example where just you added a lot of layers. You went from 20 layers of a simple CNN model to 56 layers. And you could see, again, for the training set, you should be able theoretically to reach the same accuracy, but it's not happening. Okay. So the idea of ResNets, or residual networks, is to address this issue by having doing a small trick. The trick is to add these shortcut connections, or skip connections, sometimes they're called, around the convolutions. And for example, here after 2 convolutional layers, so this would be a 3x3 kernel with 64 channels or 64 different kernels. So I have these 2 convolutions, and I'm doing, in this case, I have a 64 channel input. So I'm doing 2 convolutions, and I'm adding actually just the identity map to the output of these 2 convolutions, and then I'm applying my nonlinearity and saying that this is the output of my residual block. Okay, so this is an idea of how to skip it. Notice that sometimes, for example, you have a mismatch between channels. Like here, you have a 256 channel input, and you have this 1x1 convolution here to change the number of channels.
Was there pulling the first layer on the website?
No, this is ignoring pooling. Pooling is not relevant for this example.
How comes the first layer 64 layer?
Pooling is not on the channels, it's on the spatial extent. So it doesn't matter. You just specify the number of channels for your convolution. Okay. All right. So this is the idea of residual networks, and kind of the question is why would this actually help? Why would this help us increase the depth of the network? What do you think?
Reduce the weight that you give to this block.
Sorry?
It's like this block that you bypassed,
Mhm.
it's still there, still does
Yeah, it's there.
but you can reduce the effect it has on the output in case that it doesn't help.
Mhm. That's a good point. Okay, so that's one way to look at it. Is it kind of helps you learn identity mappings because you always have this identity going out, and it's easier to learn to do nothing. Kind of, it's easier to learn to do nothing than to learn to do an identity. You might just get very small weights that have a small effect. That's one way to see it. And another way to see it is you have a path of gradient flow that's not affected by these two convolutions. Okay, so at least to this path, the gradient will flow more freely back to the previous layer, and you kind of mitigate the vanishing gradient problem. So these are two different effects that probably work together. Okay, and that's the idea, and you will see in the homework how to implement it, and in the next tutorial also we'll see an example of using this technique.